Hello everyone, and thanks for coming. I'm very honored and excited to be here to give a presentation. So today my topic is safe harbor or hostile waters, unveiling the hidden parts of the TorchScript engine in PyTorch. So first, let me briefly introduce ourselves. So we are all security engineers from Alibaba Cloud, and I'm Jianzhou, and I completed this work together with my colleague Li Shuosong. And we were really looking forward to come here, but unfortunately, due to visa application issue, we were unable to attend the event on site. So we sincerely apologize for this, and as a result, we have to share our presentation through this pre-recorded video. And if you have any questions about this topic, feel free to contact us via Twitter. So here, this is the agenda. So first is the introduction and background knowledge, and then I will introduce where the story begins, and after that, I will analyze how this only works and analyze the TorchScript engine, and finally is the impact of this vulnerability and some defense recommendation and summary. So first, introduction. So what is PyTorch? PyTorch is a machine learning framework based on the Torch machine learning library, and it was developed by Facebook, and now it is an open source project, and it is very easy to use and has some really great features. And PyTorch is widely used in the deep learning research and natural language processing, or called NLP, and computer vision. But to be honest, in the field of machine learning, and there are many popular frameworks and well-known projects like TensorFlow and Perils. However, according to the official paper with code website, and you can see that PyTorch has undoubtedly been the most popular machine learning framework. And so if someone can find some bugs in such a famous machine learning framework, and that will be a really cool thing. So next come to the second part, where it all began. So in the early days, PyTorch used pickle to load and save models for convenience. But however, pickle is one of the most well-known security issues in Python, and in fact, the official Python document warns that using pickle can be unsafe, and especially when loading untrusted data. So in 2021, and someone raised this issue on GitHub and called for a solution to address the pickle issue. And finally, in 2022, and PyTorch released a notable update that introduced the wait-only parameter. So let's briefly analyze the implementation of wait-only, and as we can see that when wait-only is not enabled, and this is by default, PyTorch will use pickle to save and load modules, and which introduce security risks. And however, when we set a wait-only parameter, then it will use something called wait-only and pickle, and this is a restricted pickle to load the model. And here, let's try to use the wait-only, and you can see that by default, the wait-only is set to false, and we can easily RCE via a evil pickle module, and you can see that we just use this reduce magic method, and we will execute a whoami command, and we save the module and load the module, and you can see that we successfully executed the command, and we get the result root. However, when we use wait-only equals true, and it just with the exception, and it seems that the vulnerability is effectively mitigated. And also on the official PyTorch document, you can also see that they consider wait-only equals true is safe, and at the same time, they just warn that loading untrusted checkpoint with wait-only equals false must never be done. And additionally, when similar security issues are discovered in other PyTorch-based components, they often fix it by using wait-only equals true, and here is the example. Initially, VLM will use torch.load without wait-only equals true, and which introduce a security risk. And then they just patch this vulnerability by adding the wait-only equals true parameter. So not only VLM, in general, whenever a software is found to be using torch.load without wait-only equals true, and the fix is always the same way, just adding this parameter. But here comes the question, can we blindly trust the security of wait-only? So next we will dive deeper into how wait-only works. And earlier we pointed out that withholding is something like a restricted pickle. So before we analyze how withholding is implemented, we need to understand how pickle works. So pickle is just like an interpreter, and it reads and interprets each opcode in sequence, executing the corresponding operation. So here in this case, we first encounter the global opcode, and it will execute the load global function. And here it will just load the target function. And so for example here, we will load the system function and we will push it onto the stack. And you can see here. And then since we get the function and we need to construct the parameter. So first we will execute the Unicode opcode, we will execute the load Unicode function, and it will read a string. So here it is one my command, and since the command must be the turbo, so we need to wrap this string into a turbo format. So we just add a turbo1 opcode and we will execute the load turbo function. So you can see here, after we execute the load Unicode function, and we will push the one my string onto the stack, and after we execute the load turbo1 function, and it will wrap the one my string to a turbo and push it onto the stack. So finally, since we get the function and its parameter, and we can execute this function. And so here we will use the reduce opcode, and it will use the reduce function, and you can see here it will get the argument from a stack, get the function from a stack, and execute, and we can achieve command execution. So how does withholding address this issue? And through the above example, and we can roughly sense that the most dangerous part of the pickle deserialization is load global and load reduce. So the withholding and pickler just add some restriction to this dangerous opcode. And looking at the code, you can see that the load global function just adds some whitelist and blacklist check to prevent a security issue. And also load reduce function is restricted in a similar way, and you can see that it has a whitelist. So in general, withholding is implemented using a whitelist and a blacklist. So how can we bypass? And a common approach is to analyze the whitelist and check if there are any potential dangerous opcode. And I did the same, but I didn't find anything useful in the end. So we are often limited by the fixed way of thinking. So for example here, most of us may only see the obvious whitelist and the blacklist mechanism and just stop here. However, in reality, the loading process of torch.load with withholding equal true is quite complex. So is it possible that there might be some issues elsewhere in this loading process? So I try to conduct a complete analysis of the withholding workflow to ensure nothing is missed. So I started analyzing the entire workflow, and I just stepped through the code and debugging line by line. And during one of my analyses, I found this something strange, and you can see that torch.g.load. So what is that? And I have no idea with that, so I just searched on the Google, and you can see that torch.g.load is used to load the module in the TorchScript format. So now you can understand why we named this topic. Yeah, we will analyze and exploit the TorchScript engine.
Hello everyone, this part will cover the basics of TorchScript and its code implementation. TorchScript is used for deploy model in environments without passive interpreter, such as CPP and mobile. It can be compiled from Python code through scripting or tracing, and saved as PT file, which can be loaded and run in CPP and mobile. The save and load process involve serialization. I will explain how Python code is compiled to TorchScript, the serialization and deserialization process, the structure of PT fields, and finally how it executes. First, we can use TorchGIT script decorator to script one Python function to TorchScript. The steps to compile are: first, press Python source code into a Python ST. Second, convert the Python ST to a GIT ST. Third, transform the GIT ST into an IR graph. The AR graph initially contains many unnecessary nodes, which are eliminated through optimization to make it more concise. Let's take a deep look about the compile process. Before we start, I need to show what is function and model in this context. You can see that one is function, the other is a class. The scripting process for these two are somewhat different, so we will introduce them separately. Let's look at the function first. The compile process is handled within the script MPL function. There are two main functions, getJIT_def and JIT_script_compile. The getJIT_def function performs two main tasks. First, it uses the AST library to convert Python code into a Python AST. And second, it calls build_dev to transform that Python AST into a self-implemented JIT_AST. JIT_script_compile is a function born from CPP to Python, which is a implementation in the CPP layer. It further converts the JIT_AST to IR within the CPP code. It eventually invokes the toIR function, which finishes the transformation from JIT_AST to IR. Additionally, the toIR will also call some optimization functions to simplify the IR graph. Now the function compile process is done. A high-level understanding of the process is enough for this sharing. If you are interested in the complete source code details, you can use the caustic I have provided to navigate through the source code. Then let's look at the model. The overall process is similar to that of functions. Expect there is an additional step at the beginning. Retrieving all functions from the model. It needs retrieve functions and compile functions one by one. The stops fn function is responsible for handling this. Stops fn is analyzed for infer methods to compile in this context. Let's see what the infer methods to compile function does. In the infer methods to compile function, it first uses dir to get all attributes and methods of the model. After filtering, it saves the methods and need to be exported, thereby collecting all functions in the model that require completion. Make stop from method converts the collected functions into JIT_AST using the getJIT_def function, which is the same one used during function completion. Back to create a script model MPL. The method stops variable stores the JIT_AST we just converted, and the create methods and properties from stops function takes method stops as input and is responsible for converting it to IR. We can see that this call stack is similar to the call stack for function completion. Both eventually finish the conversion into IR function. Now the model compile process is done. Overall, some key steps are the same for function. Both use getJIT_def to convert Python to JIT_AST, then convert it to IR through to IR. The serialization feature can save models and deploy them to other environments. Use TorchScript to save model as a PT file. Use torch.load to load the PT file as a model. The Python code here is converted from IR. You will notice it's slightly different from the original code. Let's see how script function script model is serialized. Script function has an additional step compared to script model. It needs to be converted to script model first. After that, both call serialize for serialization. During the serialization process, some information is stored in the data pickle and constant pickle in pickle format. Additionally, it saves the Python code converted from AR and debug information to the code folder. To summarize the save process, the touch function first converts it to touch model. The remaining process is the same. First, the I value corresponding to the model is serialized in pickle format as a data pickle. Second, obtain the code and debug info via Python print and write to code directory. Third, save tensor constants to constants PKL. Now the serialization is done. Let's look at the detail of the PT field. The PT field is compressed achieve using zip compression. The field tree after decompression is shown above, and we can use pickle tools to disassemble it. Above is the disassembled output of data pickle. The meaning of this pickle code is create an object named touch placeholder model and set its training attribute to true. And the touch placeholder model object is a script model. So when interpreting data pickle, script model object is create. The constant pickle contains pickle code, which can create a value object with tensor. The touch py field contains Python code strings. It's the same as the content of the code attribute in script model because they are obtained in the same way. Okay, now we understand the three most important parts saved in the serialized field: data pickle, constant pickle, and the source code in the code directory. Let's see how these parts are restored into a script model. We can see that in the deserialized function, the three main parts of the serialized field are converted into a script model. Let's look at the function implementation. Deserialize will call read achieve to read constant pickle and data pickle. Then we'll get one model in CPP, which is the script model in Python. During the deserialization process, first unpickling constants pickle to obtain tensor constants, then save in constants table. Second, unpickling data pickle. During the process of unpickling data pickle, relevant source code is read from the code directory and pressed as needed. And related constants are also read from constants table. The code pressing process includes converting Python code to custom tokens and then transforming tokens into JIT, AST, and finally into IR. This process differs significantly from the earlier Python to touch script completion. To summarize the load process, first, reach main logic via deserialize. Second, call read achieve to read constants PKL. Convert constants to I values by unpickling and save them to constants table. Third, call read achieve to read data PKL. restore corresponding values by unpicking. Fourth, during data pickle unpicking, source importer reads code fields and constant table to restore IR through press tab, find named tab, to import named tab. Now the deserialization is done. Let's take a look at how TorchScript is running. The IR graph consists of many nodes, and every node contains three parts: in, output, and opcode. Opcode is the key to execution. The process of executing TorchScript is to iterate through the IR and convert it into instructions, then interpret the instructions. Every instructions have one opcode. There is a switch table here that finds the corresponding process logic through the OP and then executes it. Now we have a basic understanding of the TorchScript workflow. While reading the code, I discovered something interesting. There is one opcode named OP, and it can do a call on operator table. The operator table contains many functions corresponding to operators. I'm curious about what operators they are. Some built-in functions register themselves as operators, requiring OP instructions to call corresponding functions. And the register operators class manages these operators and registers them by register operator function. I pitch the Python code and add one function to output all operators. You can see there are over 2,000 operators here. Are all these operators safe? During our code audit of these operators, we discovered two interesting operators, save and from fill. Here we can see the corresponding implementations of these two functions. The save function will save specified value as a model to specified fill. This can lead to arbitrary fill rate. But the saved field contains a lot of dirty data which model information. The from field function will read the field which I specified and convert the field content to tensor, then return the tensor. We can get the field content from the tensor. Now we know these two operators have vulnerabilities. But there is still a problem: how to call them from TorchScript. To get the answer, we need to first understand the operator registration process. The get built-in table function registers some object member functions to built-in ops. And during this process, it also adds prefix to the member functions for rename. Finally, the address of these functions and their modified names will be placed into a built-in table. During the TorchScript compilation process, the two sugar value will be triggered, where it checks whether the Python object exists in built-in table. If it exists, it returns a built-in function. Finally, this built-in function will be inserted into the IR graph through emit built-in call. Back to the built-in registration process. We now understand that item save may come from one of these objects in models containing built-ins. By testing each object individually for the process of a save function, we will find that the save function exists in the touch object. Item from field can also be obtained in the same way. So we just need to call touch save or touch from field to get arbitrary field read write ability in TorchScript. Now we can try writing a field to get RCE, but since there are some dirty characters, only specific special fields will work. The Ubuntu clone type failed because of a permission mismatch. Our script uses TouchSafe, which writes fields with 644 permissions, but the colon daemon requires 600. Here is one poke video. You can see we get RCE. The vulnerabilities we have discussed so far might be more similar to logic vulnerabilities. On the other hand, some hackers may prefer memory-related vulnerabilities. We have also discovered a few overflow issues. Here you can see that when we load this model field, it triggers a heap overflow. As a result, we can observe that heap address and the loaded address of the library are leaked. This is one poke video. But due to time limit, we won't go into them in great detail here. We hope to share them in the future. Okay, this is the full details of this CVE. The fix is also relatively simple. It prevents the use of TorchScript when wets only is enabled.
So next, what is the impact of this vulnerability? And the entire AI ecosystem is just like this house, and the PyTorch is the fundamental components. And if there is an issue with PyTorch, and just like we have removed one of the bottom level components, and the security of the entire structure is then compromised. And we did a simple search on GitHub for projects using this only equal true, and you can see that a lot of projects use it in this way. And here we select two well-known projects as examples to illustrate the impact of the vulnerability, and one is VLM and the other is Transformers. So what is VLM? And VLM is a high-performance library for large language model inference and optimized for speed and memory usage. And so why did I choose it? Because in fact, it happened to have a CVE, and the CVE just said that it used torch.load function without with only equals true, and which has a security issue. And they just patched this vulnerability by adding the with only parameter, and this seems to solve the problem, but because of the PyTorch issue, and all mitigations end up being ineffective. So the safe harbor we once thought was actual hostile waters. Also, at the same time, I noticed a very interesting phenomenon, and you can see that in the requirements cpu.txt, and you can see that it just hard-coded a PyTorch version, and also in the GPU version, and you can see that it also hard-coded the PyTorch version. Hey, so what does this mean? And it means that even if PyTorch released a new patched version, and users of VLM cannot update timely because VLM has hard-coded this version. As a result, they will remain exposed to this vulnerability for a long period. And first, let's set up our environment. And since the latest version of VLM has already fixed this issue, and we need to install an old version, exactly 0.7.3, and you can see that when we install VLM, and it will install the old version of PyTorch. And so here, we will use this function as an example to demonstrate the existence of the vulnerability. At first, I didn't think too much about that. I just want to take the poke from the previous vulnerability and use it right away, hoping for a one-shot success. And you can see here, when we enter the logic we want, it will definitely load our model. So will we succeed? But in fact, just failed. So why? And let's take a look at the previous poke, and you can see here, after loading the model, and we need to invoke this model in order to trigger the forward logic. But here, after we loaded the model, and you can see that it doesn't invoke the model, it just gets the items attribute and then delete this model. So is this really the end? But however, at that point, I noticed the exception message. It just said that the model object don't have the attribute named items, and this error message just provided me with some inspiration. So item is essentially a keyword in Python and commonly used to iterate our dictionary type objects. As you can see here, in fact, item is a function. So can we spoof the function name? And so I made my first try, and however, when we write the code in this way, I just changed the function name from forward to items, and I run the code, but you can see that we still get this error message, and why it is still saying that we don't have the item attribute. But however, I try to write it in this way, and we just call the items function in our forward message, and you can see that when we run the code, and we successfully trigger the logic. And so this was very, very strange, and the reason is that when we retrieving the model functions, it defines whether this function needs to be exported. For function not decorating as export, and there is a lazy export strategy, so meaning that they are only exported if called within export functions. So here you can see that in the left picture, and you can see that we just degraded the item function with torch.load.export. So here the object, the model will have the items attribute, and in the right window we don't decorate it with torch.g.export, so we need to call it in the exported function. So in this way, and the object will have the items function. And if we don't do that, our object will not export the item function, so it will definitely not find this attribute. And in the end, we report this vulnerability to VLM, and they highly acknowledged our work. And you can see that the team member just said that this is very interesting because PyTorch document just claim it safe. And the patch is very simple. You can see that it just changed the version of PyTorch. And the next is Transformers. So Transformers is a very popular open source library made by Hugging Face and provides pre-trained models and tools for natural language processing tasks using transformer-based architectures. And also you can see that Transformers also implemented some security hardening measures for torch.load, and you can see that it by default will use with only equals true. And first, let's set up our environment. Since the latest version of Transformers has already fixed this issue, we need to install the old version 4.51.3. And this is the official usage guide for Transformers, and you can see that we need to load the module and create a pipeline, and then we can start having a conversation. So for example, we can ask the secret to baking a really good cake is, and it will get an answer, and to use the right ingredients and follow the recipe. And here you can use my demo report, and you can see that my report only has 3 fields. One is readme, and another is configured JSON, and I also have a field named PyTorch model.bin, and this is a test PyTorch field. And if we run the code, and it will finally call the torch.load to load our evil model. And let me introduce the code, and you can see that when we're loading a remote report, and it will load a remote model, and by default fields in SafeTensors format or in PyTorch format are allowed. And like the previous vulnerability, and it will invoke the keys function. So here we can just spoof the function name to keys and save the model in our local report. And then we just load the local report, and you can see that, of course, we can exploit it. And then I just report this vulnerability to Hugging Face, and you can see that it just fixed it. And they fix it. The patch is very simple, and you can see that it just checks the PyTorch version must be greater or equal 2.6. And finally, is some defense recommendations and a summary. So if you are still using an old version of PyTorch, please update now. And here is also some recommendations. So for the model format perspective, and you can see that we should use more secure format like SafeTensors. And also from the model community perspective, we need to scan and flag malicious models. And also Hugging Face has already done the relevant works. And from the user perspective, we should not load untrusted model. And it is better to load this model in the sandbox. So any questions? And thanks again for listening. And if you have any further questions, please feel free to contact us at any time.